4 light years away, there's a planet that might actually be capable of supporting life. And right now, after everything humanity has ever built, ever launched, ever engineered, we are not even remotely close to reaching it. Not with rockets, not with anything sitting on a drawing board today. Before I explain exactly why, hit subscribe right now, because the actual answer scientists give for this is more frustrating and more shocking than most people expect. Stick around for the whole breakdown. This is not some distant, half-imagined world buried deep in a far corner of the galaxy that nobody will ever seriously think about reaching. This is our literal next-door neighbor in cosmic terms, the closest planet orbiting the closest star system to our own sun. And we still cannot get there. Understanding exactly why reveals just how enormous the gap really is between where humanity stands today and where we actually want to go. The planet in question is called Proxima B, and it orbits a small, dim red dwarf star named Proxima Centauri, which happens to be the nearest star to our sun in the entire universe. Scientists confirmed its existence back in 2016 using extremely precise measurements of tiny wobbles in the star's light caused by the planet's gravity tugging on it as it orbits. Proxima B sits inside what astronomers call the habitable zone, the narrow range of distance from a star where temperatures could theoretically allow liquid water to exist on a planet's surface. It is roughly similar in mass to Earth, and that combination, rocky, roughly Earth-sized, sitting in the habitable zone of the nearest star system we have, is exactly why it instantly became one of the most talked about exoplanets ever discovered. It stopped being just another distant point of light in a telescope readout and started becoming something closer to a genuine long-term objective. Something engineers sketch mission concepts for, something scientists write serious funding proposals about, something that occupies real institutional attention rather than existing purely as a curiosity for people who like looking up at the night sky. So here is the obvious question. Given everything humanity has built so far, is actually getting there even possible? The short answer scientists give is no, not with today's technology, not by a long shot. And the longer answer is where things get genuinely shocking. Because the obstacle is not really about not knowing where Proxima B is, or not having powerful enough telescopes, or even not understanding the physics involved. We understand the physics extremely well. The problem is that the physics itself is brutally, almost comically unforgiving once you start doing the actual math on distance, speed, and fuel. Let's put the distance in real terms first, because a light year sounds abstract until you convert it into something more familiar. Proxima Centauri sits about 4.24 light years from Earth. That translates into roughly 40 trillion kilometers, or about 25 trillion miles. Humanity, meanwhile, has not even managed to send a single human being past the moon in more than 50 years, and the moon sits a mere 384,000 kilometers away. Voyager 1, humanity's most distant spacecraft, and arguably its single most impressive achievement in deep space travel, has been continuously operating since 1977, nearly half a century of non-stop flight. It currently travels at roughly 17 kilometers per second, covering around 540 million kilometers every year, which is genuinely remarkable by any ordinary standard. And yet, at that exact pace, it would take Voyager 1 somewhere around 73,000 years just to cover the distance to Proxima Centauri, assuming it was even pointed in that direction, which it is not. Humanity's greatest deep space achievement has still only barely poked past the outer edge of our own solar system's gravitational influence. Nowhere close to genuinely interstellar territory in any meaningful sense. That single comparison alone tells you almost everything you need to know about the true scale of the problem. To make a trip to Proxima Centauri realistically achievable within something resembling a human lifetime, spacecraft would need to travel at speeds that go far beyond anything humanity currently has any ability to produce, based on the physics of how long onboard instruments can realistically survive radiation exposure and mechanical degradation across a multi-decade flight through the vacuum of interstellar space. Most researchers place the bare, minimum realistic threshold somewhere around 10,000 kilometers per second. At that speed, the spacecraft could reach Proxima Centauri in roughly 130 years, which is still longer than almost anyone actually lives. Push the speed up to 25,000 kilometers per second instead, and the travel time drops to somewhere around 50 years, which finally starts to sound like something a single human lifetime could conceivably encompass. These numbers are not arbitrary. They come directly out of the underlying physics governing spacecraft durability, communication equipment reliability, and radiation tolerance over decades-long journeys through deep space. And here's where the genuinely shocking part of the answer comes in. To reach even just 1% of the speed of light using conventional chemical rocket propulsion, the exact same basic combustion technology every rocket humanity has ever launched relies on, you would need more than 1,000 trillion kilograms of fuel for every single kilogram of spacecraft mass. Sit with that ratio for a second, because it is almost impossible to picture on an intuitive level. Translated into something more concrete, that fuel requirement works out to a spacecraft roughly 100 times more massive than the entire planet Earth. Not 100 times heavier than a large rocket, 100 times more massive than our entire planet. An amount of raw material so enormous it would essentially require dismantling several planet-sized bodies just to gather enough propellant for a single launch. That is the actual literal physics answer to why chemical rockets, no matter how much we improve their efficiency or scale up individual engines over the coming decades, are already permanently crossed off the list of viable options for interstellar travel by virtually every serious researcher in the field. It is not a limitation of current engineering skill. It is a hard physical wall built directly into the chemistry of combustion itself. That single fact forces scientists into a series of genuine concessions if humanity is ever going to seriously attempt reaching Proxima B. The first concession is that actual human astronauts are almost certainly off the table for a first mission. A crewed mission would require dramatically more mass, more energy, and more onboard resources than an unmanned alternative. And it would also need a fully self-contained life support system capable of functioning flawlessly for well over a century with zero possibility of resupply or repair from Earth. An engineering requirement so extreme that most mission planners consider it effectively impossible with anything resembling current or even near future technology. An automated probe, by contrast, only needs its instruments and communication systems to keep working, which is a dramatically lower bar to clear. The second concession is the mission goal itself. Rather than attempting to slow down, enter orbit around Proxima Centauri, or land on Proxima B directly, the realistic version of this mission is a flyby, a probe that simply streaks straight through the system at enormous speed and gathers as much data as possible during a brief window before continuing onward into deep space. That single change removes an enormous amount of engineering complexity. There is no need to design a braking system capable of surviving deceleration from a meaningful fraction of light speed. No need to figure out how to settle a probe into a stable orbit once it arrives. Just fly through, gather data, and transmit it home. That shift alone turns an almost impossibly complex mission into something considerably closer to achievable within a human timescale. So what propulsion technology could actually get a probe moving fast enough to make any of this worthwhile? Ion and plasma engines are usually the first thing that comes up, and they have already flown successfully on multiple missions closer to home within our own solar system, offering continuous, steady thrust over extremely long periods and far greater fuel efficiency than chemical rockets. Nuclear thermal engines, which use onboard reactors to heat propellant gas and expel it with considerable force, are another serious option. Both represent real, meaningful improvements over chemical propulsion. But even pushed to their theoretical limits, both technologies would still take more than 40,000 years to reach Proxima Centauri, which is nowhere close to a workable mission timeline for any human institution. A 40,000-year journey might as well be permanently impossible, because no government, organization, or civilization in human history has ever maintained a single continuous, coordinated technical project across anything remotely close to that span of time. A more promising development comes from something called the VSIMR engine, short for Variable Specific Impulse Magnetoplasma Rocket, developed by the Ad Astra Rocket Company under the leadership of former astronaut Franklin Chang Diaz. VSIMR is a plasma-based engine with real potential to dramatically shrink travel times within our own solar system. It could theoretically cut a crewed mission to Mars down from roughly 18 months to as little as 39 days, which would be a genuinely transformative leap for solar system exploration. But scaled up and pushed to its absolute theoretical limits for an interstellar mission, VSIMR would still take somewhere around 2,200 years to reach Proxima Centauri. Better than tens of thousands of years, certainly, but still dramatically beyond the span of any human lifetime, or any human institution's ability to maintain a project across that time frame. This is where a genuinely different approach enters the conversation, one that abandons the idea of pushing a heavy, conventional spacecraft to extreme speed, and instead rethinks the entire shape of the mission. It is generally known by the name Breakthrough Starshot, a real, currently funded research initiative exploring whether a fleet of tiny, gram-scale probes, each attached to an ultra-thin, ultra-reflective sail only a few meters across, could be accelerated to a meaningful fraction of the speed of light using a massive, ground-based array of lasers. The concept works by firing an enormous, precisely coordinated burst of laser light at the sail for just a few minutes, pushing the probe to speeds potentially reaching around 20% of the speed of light. At that velocity, a probe could reach the Proxima Centauri system in roughly 20 years rather than millennia, a timeline that actually falls within a single human career, let alone a lifetime. The trade-offs here are significant, though, and this is part of what makes the whole approach feel almost fragile by design. A probe that's small and that thin is extraordinarily vulnerable to collision with even microscopic interstellar dust particles. Along the way, any one of which could disable it at those speeds. Breakthrough Starshot compensates for that risk purely through sheer numbers, launching an entire fleet of thousands of individual probes simultaneously, so that even if a large portion fail to survive the full journey intact, enough would realistically make it through to call the mission a success. It is essentially the same underlying strategy nature uses across countless biological systems. Redundancy and volume compensating for individual fragility, trading the comforting idea of one heavily armored spacecraft for the statistical resilience of an entire dispersed swarm. Each surviving probe would carry its own miniature laser communication system designed to beam whatever data it collected back across 4 light years of empty space to Earth, though even that final step comes with its own brutal cost. A radio or laser signal traveling at the literal speed of light would still take just over 4 years to make that one-way trip home, meaning humanity would receive its first close-up look at Proxima B roughly 24 years after launch, and would not even know for certain the mission succeeded until that signal finally arrived. Several early-stage prototype tests for exactly this kind of laser sail technology have already quietly taken place here on Earth. Small-scale laser propulsion demonstrations and material testing for the reflective sails themselves. None of it guarantees eventual success, and the full-scale ground laser array required would be a genuinely massive, expensive piece of infrastructure that does not exist yet in anything close to the necessary form. But it represents real, tangible engineering progress. Rather than pure speculation on a whiteboard and with sufficient sustained funding, some researchers believe a mission built on this basic concept could realistically launch within the next few decades, potentially within the working lifetime of people alive today. Even setting aside the question of whether we ever find any confirmed evidence of life on Proxima B, a successful mission of this kind would carry enormous scientific value on its own. It would let researchers study, up close, how a rocky planet actually forms and evolves around a small, dim red dwarf star, a category of star very different from our own sun, and, as it happens, the most common type of star in the entire galaxy, Proxima. Centauri itself is known for violent, unpredictable flares of radiation, powerful enough that some scientists question whether Proxima B's atmosphere, if it even still has one, could have survived billions of years of that bombardment intact. A close flyby could help answer that question directly rather than through distant telescope inference and modeling alone, and in doing so tell us something much broader about how common or rare truly habitable worlds might be around the kind of small, dim stars that make up the overwhelming majority of stars in our galaxy. Before Breakthrough Starshot came along, scientists had already spent decades sketching out even more exotic ideas, and it is worth walking through a couple of them, because they show just how far outside the box researchers have had to think to even approach a workable timeline. Back in the late 1950s and early 1960s, a genuinely wild concept called Project Orion proposed propelling a spacecraft by detonating a rapid series of small nuclear bombs behind it, using a massive pusher plate to absorb each blast and convert it into forward thrust. On paper, some versions of Orion could theoretically have reached a meaningful fraction of the speed of light using nothing but 1960s-era nuclear technology, and serious physicists worked on the mathematics for years. It was eventually abandoned, not because the physics did not work, but because of the obvious and enormous practical problems involved in launching a vehicle that detonates nuclear devices in its own wake, along with international treaties banning nuclear explosions in space that made the entire concept politically impossible almost as soon as it was seriously proposed. A more modern and even more theoretical idea involves antimatter propulsion. When matter and antimatter collide, they annihilate each other completely, converting their entire mass directly into energy according to Einstein's famous equation relating mass and energy, making it the single most efficient fuel source physics currently allows for. A spacecraft powered by antimatter annihilation could, in theory, reach a significant fraction of light speed using a fuel mass thousands of times smaller than anything chemical propulsion would require. The catch is that humanity has only ever managed to produce antimatter in quantities measured in nanograms, at enormous cost, using some of the largest particle accelerators on the planet. Producing even a single gram of antimatter, nowhere near enough to power an actual interstellar mission, would take existing facilities an amount of time measured in decades and a budget that no space agency on Earth currently has any path toward funding. It remains one of those technologies that is completely valid on a chalkboard and completely out of reach in any laboratory that exists today. All of this helps explain why, when serious researchers rank realistic near-term options for actually reaching Proxima B within a human timescale, something like Breakthrough Starshot keeps rising to the top of the list. It does not require inventing new physics. It does not require detonating nuclear weapons in orbit or manufacturing antimatter by the gram. It requires scaling up laser technology, sail materials, and guidance systems that already exist today in smaller, less powerful forms, which is a very different kind of engineering challenge than one that depends on a breakthrough nobody has achieved yet. There's also a piece of this problem that rarely gets enough attention, and it has nothing to do with propulsion at all. It is the sheer patience the mission demands from everyone involved in building it. A probe launch today using laser sail technology would take roughly 2 decades to reach the Proxima Centauri system, and then just over 4 more years for its data to crawl back to Earth at the speed of light. That means the scientists who design, fund, and launch a mission like this may well be retired, or in some cases may not even be alive anymore, by the time humanity actually receives the first close-up images of Proxima B. Every engineer working on the project has to accept from day one that they are very likely building something whose payoff belongs to a future generation rather than their own. That kind of multi-decade institutional patience is genuinely rare in human history, and some researchers argue it is just as difficult a problem to solve as the propulsion itself, because funding priorities, governments, and entire space agencies can shift dramatically within the 20-plus years a single mission like this would need to unfold from launch to final data return. There is also a broader, more philosophical piece to why scientists keep pushing on a problem this difficult, despite knowing full well that no version of this mission happens quickly or cheaply. Reaching toward Proxima B is never really just about scientific curiosity for its own sake. It increasingly gets framed by researchers and mission planners as something closer to long-term insurance for humanity as a species, a hedge against the uncomfortable fact that a civilization confined permanently to a single planet remains fundamentally vulnerable to any single catastrophic event capable of ending it all at once, spreading outward, even slowly, even imperfectly, even starting with nothing more than a swarm of gram-sized probes drifting past a single rocky world 4 light years from home, represents a kind of insurance policy that simply cannot be built any other way.